Cardiovascular disease, a disease which involves the heart and blood vessels, is the largest cause of death in the world. Just how many people is that, I hear you ask?
How many is that?
Well, it's over 18 million people per year, according to the World Health Organization. That's roughly the population of the Netherlands.
That's crazy.
It sure is. Most of these deaths come from disease of the coronary arteries, the arteries which surround the heart and often lead to a heart attack. Being able to predict this is one of the holy grails of the field, but there is still much to discover before we reach that milestone. In particular, we don't yet fully understand how the blood flow, the heart, and the artery interact with each other and how this affects the stress field within the artery, which in turn can impact how a heart attack occurs. To investigate this, we need an inside look at the arteries, and one of the ways to get this is using invasive angiography. The problem is that angiography can only peek at what is going on inside, and we need more information on what mechanisms are really at play. This is why we need to reconstruct a three-dimensional computer replica of a patient's exact artery, which we then analyze using a technique called fluid structure interaction. As the name suggests, this technique allows us to simulate how blood flow and artery structure interact with each other to find areas that could be at risk of disease. And these results look something like this.
Cool.
We also analyze wall shear stress, which you can see here. Now this is a measure of friction stress in the blood that is immediately next to the artery wall. So this wall shear stress has been shown to have links to the accumulation of small fatty particles called low density lipoproteins, so it's important in understanding how disease progresses. We can then plot this over time at different points in the artery.
Do we really need to include all these little side branches though?
Good question. Yes, we do, as they help regulate blood flow. And if we don't include them, we see wall shear stress do something like this. We also see how the structural stress in the artery wall changes by calculating what is called the von Mises stress. We can see that the artery is pushed around by the beating heart, resulting in these intense stress areas in red. Now, if we look at this stress with respect to time and compare the results with a model that does not include how the heart beats, we can see a significant change in results. Now, this shows how fundamentally important the heart motion is to potential heart attacks. With further research and development, we anticipate that this type of fluid structure interaction analysis could become commonplace in helping predict how disease and heart attacks occur.